Good afternoon, everyone. My name is Maria Coliu, and I'm an associate professor at the Zachry Department of Civil and Environmental Engineering at Texas A&M University. I would like to welcome you all to the 2024 ASE Engineering Mechanics Institute Objective Resilience Committee's lecture. It is my pleasure to introduce this year's speaker, Dr. Božidar Stojadinovic, the Chair of Structural Dynamics and Earthquake Engineering at the Swiss Federal Institute of Technology, ETH, Zurich, and a member of the ETH's Risk Center. After graduating from the University of California, Berkeley, with a PhD in 1995, Dr. Stojadinovic was a professor at the University of Michigan and the University of California, Berkeley, before joining ETH in 2011. He's an American Concrete Institute Fellow and the recipient of the 2004 ASE Walter L. Huber Civil Engineering Research Prize and the 2017 ACI Chester Paul CS Award for Excellence in Structural Research. Professor Stojadinovic's main research is in the field of community resilience, focusing on performance-based probabilistic resilience evaluation and design of civil infrastructure systems, buildings, and bridges. In his second research area, Professor Stojadinovic is using performance-based design principles to develop new response modification techniques, such as rocking for seismic protection of civil structures, assets, and to develop new methods for seismic design of structures. His third research area is focused on multi-physics and stochastic extensions, the hybrid simulation method for evaluation of the response of civil structures to dynamic excitation using hybrid models. To date, he published his work in more than 350 publications. At ETH, Professor Stojadinovic teaches on courses on seismic design, structural dynamics, and theory of structures. At the University of California, Berkeley, and the University of Michigan, he taught courses on design of steel structures, experimental methods, finite element methods, earthquake engineering, statics, and mechanics. To date, he graduated 43 doctoral students. Professor Stojadinovic will present today on actionable resilience, discussing on how we can build on the methods and practice of performance-based design to develop the principles, methods, and practice of resilience-based design, and thus make resilience actionable. Without further ado, please join me in welcoming Professor Stojadinovic for the 2024 ASE Engineering Mechanics Institute Objective Resilience Committee's lecture.
Thank you, Maria. Thank you for this nice introduction. I don't know if it's if the sound is okay online or not, but if it's not, then please say something or do something. Let's see if this is going to work. Yes, it is. What I will try to do today is to present my view on the topic of resilience and how we may be already in a situation which will lead us to doing resilience in practice as opposed to doing it in research. So the topic of resilience in civil engineering started in earnest with Katrina, with the 2005 hurricane there, and the way that it affected New Orleans. And yes, the 2005 pictures are terrible, but the 2015 pictures, this one here, shows us the recovery of that region. And recovery does happen. And the same thing we can see in Christchurch after 2011, 2012 earthquake sequences. The way that that city adopted, changed, is developing and living now continuously. And so when we talk about resilience, there are many definitions. There is even a presidential definition here in the US. But whatever they are, this resilience thing is a process. It is not a static situation that we have. It is a process of the acceptance, absorption of losses after an event in the immediate aftermath, and of recovery in the longer aftermath, weeks, months, years, that lead to adaptation of a particular region or a particular structure to the effect of the disaster, the effect of the event, and improvement, or perhaps collapsing and just not being there anymore. And so this understanding of resilience has been around at least since 2005, and in the civil engineering community probably since then, probably a few years later, but it's already been 10, 15 years that we are doing resilience-related research. And it's time now for action. And one of the impetus for action is this US Community Disaster Resilience Zoning Act, enacted very late in 2022, that designates 483 zones, counties in the US, and you can see them here on this map. These blue areas, for example, these ones are quite big, but a lot of them are on the East Coast, some are here near Houston, and so on, as particularly vulnerable and particularly at risk, and also particularly amenable to improvements. They will receive some funding that they're supposed to use to reduce the impact of climate change. That is the most important focus now, but also of natural hazards. And so there is a mechanism instituted in law that in this country that enables counties to do something. Are we as civil engineers ready to help them do these actions right? That is the question that I'd like to address. How can we make sure that the communities that will have this funding, that the communities that won't, but maybe see themselves as vulnerable and in need of resilience increase, how do we make sure that they are able to do something on improving their resilience and do something right on improving their resilience? And so what I will address is an engineering aspect of resilience of this process. And what I will try to do relate it to is implementation. And this graph, this algorithm on the right of the slide, is one that we are using typically in design. We have some kind of a design objective. We generate a trial design. We evaluate if that design is okay. Are these objectives met or not? And if not, we improve this design. This is a typical design cycle that we have. So going from the concept to implementation, what I'll try to say is, yes, we can go and formulate a design cycle aimed at resilience. And so let's start with the first ingredient, and that is the risk itself. So that is the effect of the event on the community and on the particular structure. And when it comes to structures, for more than 15, something like 25, 30 years, we have been discussing the concept of performance-based design. And it has to do with the recognition of the specter of damage that can happen to a structure. For convenience, we often discretize this into a few damage states, 4, 5 perhaps. But it is the specter of damage and the specter of consequences, the deaths, the dollars, and the downtime that we deal with in terms of performance. This concept of performance-based design, thought about in mid-90s, has pushed our profession from purely safety-based collapse prevention, safety factor type design through probabilistic applications of reliability towards designing for multiple performance objectives for a single structure. And this is coming into practice, is already into practice today. And there are many possible performance objectives. This slide is out of FEMA P58, and it shows that we can address the risk of casualties, that we can address the risk of inability to occupy a building after an earthquake, building downtime, initial building cost versus repair cost. And you can see how the green and the red money bags change their size, but also carbon impact, CO2 consumption due to repair or retrofit of the building. So the number of performance objectives has also increased over time and started to include a much broader set than dollars that's in downtime. And this is the framework that was developed at the Pacific Earthquake Engineering Center, but also at May and MCR centers about the same time, that describes the process of starting with the exposure, the structure that is at hazard, and then looking at the vulnerability of that structure, analyzing it, of course, looking at the damage analysis, the loss analysis, and then making decisions based on considering multiple performance objectives at the same time. And this kind of sort of framework is where we want to build on. And this is how performance-based structures is constituted today. For a specific hazard, we define the performance objectives in terms of the acceptable response limits. We develop a trial design, we evaluate the trial design. Many of you have perhaps done pushover analysis. Some of you have done multiple time history, nonlinear analysis to do this, looked at various aspects of the structure, determined if the performance is okay or not, and then perhaps change the structure to make it behave better. But what we noticed with some satisfaction is that in technically developed parts of the world where code compliance is high, we are not having as many casualties as we used to. Take the Taiwan earthquake as a few days ago. It was a 7.4 in a relatively densely populated island anyway. And even though we see similar soil and soft story collapses as we usually do, the number of casualties is much smaller than a few decades ago. And it has to do with the improvement of the buildings, but it also emphasizes another aspect of resilience, another aspect, and that is this recovery process. What we want to do is to design our structures so that, yes, they do not kill people, but also they are relatively fast and easy to recover and reconstitute their function. So functional recovery becomes an important issue. So we need to think about rebuilding from potentially collapsing situations, hopefully not too many of them. We need to think about repairs in situations when we have life safety performance, both of structural and non-structural elements. And then when we get to a situation when the building is good or many buildings in the region are just fairly okay, perhaps they don't have power or water, we need to talk about restoration of the building functions. And in that sense, the process needs to be understood, the process of recovery. And one thing that has been emphasized, and Professor Mary Comerio from Berkeley did this in late 80s, is the set of tasks that one has to do before a building repair or recovery needs to start. And those are inspections, the cleanup, the design of the actual repair, the financing and contracting of that thing, and then the permitting, and then the mobilization of the contractors. And only then can the repair start. And you can see here from damage states 1, small, 2, 3, 4, that the amount of actions that needs to happen, some in parallel, some in series, is growing. And this impeding factor structure is an important consideration in the recovery process, as it can take months to do so. And we have examples from various places where various aspects of, say, permitting, design, insurance have influenced the length of how long it takes to even start the repairs. And understanding this sequence is quite important. And to expand the performance-based engineering network, what I take here is the framework called EFREC that was developed initially by Vesna Terzic, and also my student Nikola and I worked a little bit on this lately, but it is an addition to the performance-based earthquake engineering framework that takes it from damage analysis and looks at the functional limit states of the building and looks at this mobilization time, the impeding factor time, and the repair time to functional recovery. And it is this framework similar to the ATC 138 framework, but it is something that we were good because Vesna was my student, and so we worked on this together and attached the PBE framework, attached the EFREC framework to the end of the PBE framework. And here is what happens here. Here is a 42-story building. Where did Vesna get the information about the variety of things to do? Repair of structural elements, repair of non-structural elements, climate control equipment, elevators. She interviewed people who did this after the Northridge earthquake. And these are the two Gantt charts of the sequence of activities along the height of this building that are produced within this EFREC framework that tell us how fast each one of those elements is going to be repaired. And also you can see here the different times it takes to do so given the unlimited and the limited resources in terms of repair resources, in terms of material, in terms of machinery, in terms of manpower. And so, again, looking at the resilience curve, the swoosh curve that we got used to in terms of picturing the resilience process, it can also be drawn that way and quantified quite nicely, seeing the pre-event functionality of the building, the drop in functionality, and the long-lasting drop in functionality because of impeding factors, and then the gradual recovery of that function. And so for a single structure, we can separate and insert the recovery portion into the performance-based engineering framework, keeping the exposure, the hazard, the vulnerability portions, inserting here the recovery portion, and then continuing with loss analysis that now includes the monetarization of time lost in the recovery process for the businesses in that particular building or the shelter provision of that housing provision of that building, and continue making decisions using multiple performance objectives that include the recovery aspect. So for a single building, we can clearly do this, and this is something that we can also put into the design framework, set up some recovery objectives, develop a trial design, evaluate that design. Of course, that evaluation is more involved. We need more data. I'll get to that at the very end, and see if those recovery objectives are met or not. So we can design using that process. But now when it comes to communities, when it comes to recovery of many things that are affected by a disaster, I have to emphasize the regional aspect. And a city, a community is a system of systems, and it is a spatial system of systems. And one thing affects the other, and there are important interdependencies that we need to analyze. To do this, what we started to do at ETH some 10 years ago, 12 years ago, is to discretize and develop a discretized image of the community with the buildings, with the structures, with the elements of the infrastructure system, power, water, transportation, communication, and then look at each one of those elements of the model, housing, power, water, transportation, communication, in terms of the supply and the demand. And this is important. A power system delivers a certain supply of power, but it is used only if people are still there to use that. Producing, recovering the entire system very, very quickly before the population is ready to return to houses is fine, nice, but then you have to basically ground that power. You have to slow down with that production until people come back. And this supply and demand balance is okay also for the water system and the housing, and the interdependencies can be captured using the flow models. So what we do is we understand that there are interconnects, that a house needs power and water to function, that the power system may need water for cooling, that the water system may need power for pumps. And these interdependencies can nicely and easily be represented through the supply and demand consideration. And what we do this with is this I-RECODES framework. It is the interdependent resilience consumption, demand, supply framework that looks at how much supply is available, how much demand is realized, and then the smaller of them is the consumption. And we did try this with large systems and also this small system to identify what goes on in there and look at interdependencies and these kinds of correlations between what nodes have power and whether the water system is supplied or not. What are the houses doing? Are they just shelters, or do they have utilities so that they can function? So these kinds of analysis enable us to identify elements of the swoosh curve, of the resilience curve, that are produced only and solely by interdependencies. This gray area does not occur if we eliminate interdependencies from the model, but does show that in this particular issue, the power system was unable to function because the cooling water was not available. In some other simulations, we see that the communication system, the SCADAs that now operate our infrastructure, if they are affected, then still that system is not going to work. The other thing that we did here is to look at supply and demand, not only of the resources that are needed for operation, but also those that are needed for recovery, the material, the machinery, and the manpower for recovery. And those becomes a separate set of resources that can also be tracked in the region, and their availability or not affect the recovery times. And so to apply this regionally, what we did is to combine the FREC framework n times for as many buildings as there are in the region, and then look at their recovery, not only in terms of their repairs and readiness for function, but also in terms of their demands for people, repair workers, repair materials, and repair machinery, and integrate that in this IRECode supply and demand framework to produce a regional combined analysis of the recovery of the housing and infrastructure systems. And this is one of the outputs of such an analysis. We did case studies. This is San Francisco, downtown, about 700 buildings. This was done using SimCore software and their examples, their GIS of the city, their case study earthquake there, their vulnerabilities of buildings. We used FREC to estimate repair times and recovery times. Here you can see story by story recovery of that 42-story building, and then look at how the entire region would recover. And for example, in some parts of San Francisco, we can see the rate at which the building stock in that area recovers with time. And that is assuming that there is a loss here of about 40% of the shelter capacity, beds in houses, and the recovery of that shelter capacity back up. So we can do this regionally, individually for a house, whatever the decision maker needs. But one thing for decision makers to notice is that the time to recovery here is 1,000 days. That is 3 years. It takes a long time. And so it's no wonder that after Katrina, after the Christchurch earthquake, we have had long recovery times. It is the processes of rebuilding that we are doing. Here is an animation of that same case study with a shelter supply graph on the top as to how it drops and increases, and also the demand for workers that is needed for that recovery process to go on. And so basically, if you don't have enough workers, you will slow down, your recovery will slow down. And that, I think, is quite an important piece of information for decision makers, not in the immediate aftermath of an earthquake, but perhaps a few weeks later, to know whether the local worker supply, machinery supply, material supply will be sufficient, or if they need to contract people outside, get some more help from elsewhere. And so these are case studies that I think are quite useful. And in terms of functional recovery, here is the same localities, but this is the electric power recovery. So we would know when shelter capacity is restored and when electric power would be restored to those regions. And you can see here we're talking not 1,000 days, we're talking 100 days. So there is a discrepancy in how fast we can recover infrastructure systems versus how quickly or slowly housing recovers. An infrastructure system is, well, regional, different, integrated in a different way. Houses are very one by one and very geographically distributed. And so this is something we could also think about how to synchronize the two processes. But nevertheless, we can get into a situation to analyze another problem, a more people problem, and that is the one of reoccupation of housing. So on the technical side, we can estimate when the shelter capacity will be restored, when the houses are going to be safe to occupy, when their utilities are going to be restored, when they're going to have power, water, internet. And now we can ask a question about how individual citizens or households make a decision to come back. what causes them to reoccupy their housing, what causes them to restart the infrastructure system demand and ask for power so that the power system can deliver it. And so this we model using the capabilities approach. In one of the previous lectures in this series, Paolo Gardoni's one addressed this issue, this notion of capabilities, but from the aspect of risk. And here we are thinking about how the decisions of the household to reoccupy a building is going to feed back the demand, not only for housing, but for infrastructure systems in that region. And that way we can look again at the regions of San Francisco, that same case study, and look at not the shelter or functional recovery of houses, but the actual decisions of people to come back and look at the rate and the length that the existing repaired now houses and functional houses in this hypothetical case study will be reoccupied. Here, it doesn't really only matter that the house is okay, but also matters whether this family stayed away for a long time and the children are already accustomed to the new school. That makes it less probable that they will return, and so on. So these are important aspects, and they are contained in the software that we developed at ETH. It's called PyRecodes. It's the Python version of iRecodes, and it has a GitHub page. On that page is the software itself and a bunch of papers that primarily Nikola Blagojevic wrote, and other students in my group also contributed to. So there is a wealth of resources for you to try, of course. And what we are working on is to integrate PyRecodes with the SimCenter risk, hazard, and risk analysis software. So hopefully that will be completed during this year. But moving on, the regional aspects, let's take a look at the important questions of quantification of resilience. Why is this important? At some point, we need to ask ourselves, are we happy with what we have? So we need to know how much resilience we have. And so using this supply and demand approach, we have always looked at how the supply varies, how the demand varies, what is actually consumed, this green line, and then sticking with the MCR, the famous paper whose first author is Michel Bruno, but it's a whole bunch of people from MCR. It is this area under the resilience curve, and we term it the loss of resilience, and it has here to do with the difference between the demand and supply, and it's integral over time. But what I find more useful for application, for action in terms of resilience, is the notion of the duration of the recovery. It's the notion of how long does it take us to come back to perhaps 80, 90% of the previous level. The time to recovery is also quite an important measure. It's not as complicated as this area. The area itself has funny units. It has units, for example, of dollar time, dollar seconds, dollar months, who knows what it is. But here, this is simple time to recovering a certain percentage of the previous function. And why is this good? Because we had this notion of measuring resilience is supported by the NIST 1090 document, and it was at the end of the 90s the product of the SPUR, the San Francisco Urban Resilience Project that they were doing then. And they said, well, we're going to have 3 phases of recovery: the short one, the medium one, and the long one. And time-wise, we are looking for certain amounts of recovery of pre-event services. Here are the buildings, for example. Here is the emergency housing, water, energy, and other things, and overall community recovery. And these are the desired numbers, and this is what this committee estimated are the realities. So there is quite a bit of gap that we need to close if we want to make this particular example city more resilient. And yes, we can do this within this FREC iRecodes framework and combine the view of housing, the infrastructure systems views, and fill out this table that comes from NIST, from the NIST 1090 document. Multiple performance objectives, multiple resilience objectives, each one of them evaluated separately, but the interdependence is still modeled using the supply and demand balance approach. We can also do this probabilistically. We can take a look at the hazard curve, generate a whole bunch of disaster scenarios, look at the model in each of those scenarios, look at the resilience plots for each of the systems modeled in the model for each one of those scenarios. So it's quite a data intense process, but then we can distill them in terms of the loss of resilience curves. Basically, this is similar to the risk curve that we're used to from risk analysis of a building, but now these are three-dimensional because there is also a time to recover. There is this time dimension that is added. So we can cut in terms of time and get the normal risk curves. And so one of these outcomes, for example, is what is an acceptable or what is a tolerable rate of exceedance of a certain poor, unresilient performance. Here it is measured in this loss of resilience, the area measure. We can also look at that in terms of the days to recovering of a certain percentage of a function. And so this probabilistic tool, we can fully approach the state of affairs in today's performance-based design, in today's risk-based performance-based design, and ask pretty much the same questions. And I come back to this, what is acceptable, what is tolerable, because this is also an issue about how to set the margins and where does that come from. And this is also what Professor Gardoni discussed in this seminar last time, and also an issue that is very, very pertinent if we are doing risk-based design. And here we're going to also do risk-based design for resilience. So communities need to figure out what these numbers are. But we can compute them and help them do that. So overall, there is a framework that we can use for doing resilience-based engineering. It has a same start in terms of a hazard module, an exposure module as all the other frameworks. It has a vulnerability module, now regional. We need to know the exposure of the buildings regionally, the exposure of the infrastructure systems, all of them, their components regionally. Then we move on to the repair recovery module for buildings and infrastructure systems. And then the quantification module for measuring how good or bad that region is doing in terms of its resilience. And with that in mind, yes, definitely I state and I see that there is a way to constitute a design process by specifying the desired resilience objectives, by doing a trial design, by evaluating this design, and perhaps checking how resilient that community is, and also improving its resilience. And so when it comes to improvement of resilience, this we can also see, this we can see from the case studies that we have done. And one way to do this is just to address the front end of the recovery process by making sure that the damage is less. We can make the structures, the infrastructure systems overall just more robust, reduce their vulnerability, and that works. The other thing that we can take a look at are recovery resources. And here is another one of those San Francisco case studies. A nice case study yielded a lot of useful results. And these peaks here are the times when the recovery worker supply is too small and the demand exceeded the recovery worker supply, leading to delays in recovery. So we can look at improvements, not only in terms of robustness, but in terms of providing more recovery resources or timely scheduling the recovery resources. And this graph also says that there is a saturation point. Providing an enormous amount of workers will not specifically improve the recovery time, simply because they cannot all at that same time work in the city and have enough machinery and have enough material. And so there is a point when impeding factors also affect this, when we can find what would be some kind of an average number of workers that will still enable a timely recovery, but not be too wasteful or too little with long recovery times, and also noticeable here, a large dispersion, a larger uncertainty on that recovery process. So we can, I think, complete the design cycle and address very fully in terms of the entire feedback loop, the resilience process. And so one thing that remains, and I'd like to emphasize, is the change. And speaking to people here in College Station, my wife is an Aggie. She got a master's here in '94, and that was a long time ago. And she doesn't recognize the city except for the water tower anymore. And her apartment building is gone. This city has changed. Your chairman told me that at some point then there were 30,000 students. Now there are 80,000 students in A&M, Texas A&M. So that means, very simply, that if there was a resilience assessment 10 years ago, it would not be valid today. It simply will not be valid. The hazard may not have changed, but the exposure has changed. So we also have not only just building new things and adding new people, but we also have the aging of structures. So in a city like New York, where there are a few new buildings and perhaps many are remodeled, we have this issue of aging and the use change. Some buildings used to be residential, now they're schools, or the other way around. And so how exactly do we take care of this dynamics of the environment, the dynamics of the structures, the dynamics of the society itself? The way that I propose to do this is through the process of continuous monitoring. Basically, a resilience assessment would need to be done every so often on a time scale, here 10 years, to take into account the enlargement and the change of the community. And this is an opportunity for engineers not only to gain good employment in repeatedly doing the same thing, but also to basically contribute to the urban development of the region very, very meaningfully, saying, hey, you're building in the floodplain, let's not do that. Because you built in the floodplain, we now need to take care of the water management, for example. Not such things don't exist for earthquakes, but perhaps you could suggest that more buildings could be base isolated, and so on and so forth. And how do we do this check? It is very difficult to invert the resilience design problem. Perhaps someone of you will do it in the future. I yet have not done it. So I suggest this scenario-based analysis, and there is a stress test concept that we can adopt from various other fields to imagine what would the city look like in 2045, and to stress test it for some predicted hazard, say past earthquake, because the seismic hazard doesn't change very fast, or a future 100-year flood, which is not the same as today's 100-year flood, and definitely not the same as the 10-year-ago 100-year flood. So these are the aspects of resilience, and I think through this talk I covered there is the recovery, the regional aspects, the quantification, improvement, and the change aspect, to the point that I can say that yes, the resilience is actionable. We can actually do real stuff with it. But and how? Performance-based design for risk, recovery-based design when it comes to functional recovery, regional aspects, regional modeling frameworks. IRE codes is not the one. In core at the NIST Resilience Center based in Colorado State, but many people here have taken part in that, is also a very good framework. Quantification, we have resilience metrics. We have probably too many, but we still definitely have them. Improvement, we can complete the resilience design loop, and the change itself we can handle using continuous monitoring. So the elements of the concept to implementation exist. Let me just remind you that this is not a done deal. What we have, for example, for components are hazard and vulnerability data. What we need is more recovery data. Professor Mander is here, did HAZUS version 1, I think, in late 80s, beginning of the 90s, with recovery for bridges, if I'm not wrong. There is HAZUS is in version 5 now. There is quite a lot of good data there. Start with that, build on it. Look at duration, but not only on that, but resources for recovery. Systemic models, we have normal operation models for infrastructure systems in, as they would say, peacetime. What we need is recovery operation models. What the system does when it is not fully constituted. What does a water system do when the leak rate in pipes is very high versus not too high at all? We need a lot more on exposure data itself, not in regions. We need to know regionally what are the building types, what are the archetypes there, what are the infrastructure systems types, and then most difficult, validation of those regional simulation models. We need to collect longitudinally the data on recovery. And then in terms of policies, performance-based design is a good example how we move from ideas to code implementations. And today's codes, ASC7s, the concrete code ACIs, the steel code, the ASC 41 on evaluation and repairs are performance-based. You see always the tables with performance categories to start those codes. We need something similar for resilience. And I also argue that within those resilience guidelines, we need the notion of continuous monitoring to make sure that the resilience assessment keeps up with the changes, not only in the hazard, but also in what is exposed to that hazard, in the change of the communities. So I think we are ready for action. I think that the concept is a very good one, and we worked on it for quite some time. The understanding we developed is solid. We can constitute the implementation, the design loop. We have the elements to build it. It needs to be done. It can be done. And with those tools, we can actually address the needs generated in the US by this Community Resilience Act and help meaningfully these 483 counties that are designated and will receive some funding to improve their resilience, they say for climate change, but also for natural hazards. And so this is what I hope to have convinced you in this talk. Before I end, let me thank the people who worked on it. At ETH in Zurich, it is Dr. Nikola Blagojevic, but before him, Dr. Max Didier, Dr. Lee Sun, he's now a professor in Cardiff, and Vesna Terzic, she's a professor in Cal State in Long Beach, and she worked on the FREC module. And then in Singapore, ETH has a large project there, the Future Resilient Systems Project, now in its second phase. And there, Mr. Lawrence Tsang and Mr. Hamed Hafeznia are also doing their PhDs on this topic of Lawrence on the capabilities approach and Hamed on optimization of resource distribution during the recovery process. And with that, I would like to end and thank you, the audience here in person and the audience online. And as Maria would like it, let us open the floor for questions.
Then let me take the first question, if that's okay, unless somebody else has a question. So that I'm going to use the mic so that I can be heard online as well. So thank you very much for the excellent presentation. My question is the burning question I also get when I present about resilience and large-scale simulation is, how did you address the verification and validation of community-level simulations?
So this is the burning question, and it burns because we don't have enough data. It would be really, really nice if today there was a large group, many more than you're here in the audience, and probably, I don't know, there is a bunch of people online, going to Taiwan and looking not only at what happened there, but also, are they repairing? How fast are they restoring power? How fast are people moving it back into buildings? What happens to the more damaged buildings and so on? And in Christchurch, there is quite a wealth of data that is slowly collected over time and a good good account keeping. What we did with these frameworks is we got some data from an earthquake that happened in Serbia, in a town in the middle of Serbia, Kraljevo. It was a 5.3, a small one, but the buildings are vulnerable. Some of them are basically very poor masonry or even mud. Others are, very weak reinforced concrete framing with infill. And those had out-of-plane failures and so on. And there were about 2,000 buildings that were damaged, and some of them were raised and people got moved into temporary housing very quickly. Others were repaired over time, and we could trace back the rate of this repair by the amount of bills, by the timing of the bills that were posted to the government for repair work. And there we see a correlation, but for a 4-month period. We see that there is a 4-month delay. And the reason why that happened is because the earthquake was in November and many single family homes were damaged, and those people do not have the concreting, mixing, cold weather equipment. They waited until the weather started to be warmer until March. And then they repaired fairly quickly. By June, July, they were almost all done. So a year later, the whole thing was more or less recovered. And our recovery simulations reproduce with some, of course, margins, this kind of rate of recovery. Now, what would happen if we translate this from earthquake to floods? Probably we would be wrong. We need flood data. Same for hurricanes, same for tornadoes. This is the data intensity of this process. It's a process, it's not an event. So the amount of data just multiplies with time. To validate something, we would need to follow along very tightly for years one of these events. And will we ever get the data? Probably not. What I suggest is something that the people in nuclear industry do, and that is called the separate effects simulation, where they have complicated codes that should track the thermal, the nuclear, and the mechanical aspects of the reactor, and they separately validate the thermal, the nuclear, and the mechanical parts, and then hope that the entire thing works. So we can separately validate some of our parts and hope that our resilience simulation in its entirety actually works.
Thank you for a very interesting presentation. It's very thought-provoking to think about how we can continue to extend this information to plan for future events and recovery. One thing I was curious about as you were speaking about some of the studies was how well can you define things like a power system in an area? How much information is available both, on the research side, as well as, if you were to maybe work with a community, it might be a different case. But can you comment a little bit on the uncertainty and some of the infrastructure and utilities?
Yes, thank you, Mary Beth. This is a good question, and the answer is there is an amazing amount of data, and the other part of that answer is it is very, very often hidden behind the security wall, because no self-respecting power system company or water system company is going to reveal sensitive data of their today's system. We have worked on the Shelby County example. That data is from 1997-ish. Even that is, well, old and not realistic and not complete. But models of power systems that power companies use to control them are extraordinarily detailed and very well, working very, very well for their operations. So a power system company in our power engineering center here have excellent models. What do we need to do to interface them with our recovery simulations? We don't need the entire thing. We need to be able for that model to answer a few questions. What is their supply? What is their demand at particular nodes? And if they provide us supply information, we can get the resilience assessment, but without interdependencies. If they provide us with the demand information, we can estimate the interdependencies. And if they let us down to the component level, we can do the whole thing. So it is up to the power, water, communications company to open up their resources. Security risks exist, yet from public databases, which is what some of my students did at Singapore, they reconstructed the gas network of the city of Leipzig in Germany purely from public data. So it is possible to reverse engineer that. Is that a clever thing to do? I don't know. Is that publishable? I don't know. I mean, yeah, we publish that too, but is it a good idea? So there is a limit in some sense as to how far we would like to go, considering not only our scientific interests, but also the security and safety of that community. And uncertainty in that sense. How well do people know what their systems do? Some know very well, some have no clue. In Kathmandu, my students went there, Max went there in 2016 and 17 and 18, and we somehow got a map, a plan, a drawing of their water system. And we went to look in one area where the shaking was high for a water tank. There was no water tank there. For whatever reason, they never built it, but it is on their plans. So the uncertainty can be very, very high. Generally, for water people, uncertainty about leaks is something that you would worry about in older systems anyway. But yeah, power communications with today's control techniques, they should be very, very well aware of what goes on in those systems. Transportation system is another thing we can get publicly. Street maps, Google Maps, whatever. We can even have traffic information in peacetime, in normal time. What happens in disasters? Well, we can simulate that, and we have examples from Northridge when I-10 was destroyed, and people adjusted to using the streets within a day. So it's possible to recover that very, very quickly, or reconfigure it very, very quickly.
Hello, Professor. I think in your presentation, you mentioned the concept of regional community resilience analysis. And for the resilience analysis for large communities or even regional analysis, a challenge will be the computational cost. Could you tell us a little bit more about how to reduce the computational cost when we are doing resilience analysis for large communities? Thank you.
So yes, this is also, thank you for the question, also something that we faced. The very simple model that you saw has, I don't know, 20, 30, 40 elements, not much, so it goes fast. When we started doing San Francisco, when we started doing Shelby County, the thousands of things show up. And one thing that Nicola did is surrogate modeling of certain subsystems. Basically, the development of a surrogate model is focused on reproducing the probabilistic response of a certain small amount of response quantities that you need. For example, supply and demand and some critical nodes. And the rest of that system we didn't simulate. We simulated only as many times as we needed to develop the surrogate model, and then relied on the probabilistic structure of that being correct to do more Monte Carlo analysis of a combined model. So there are ways to do this, and you do sacrifice some accuracy, but with the surrogate modeling techniques as they are developed today, it is possible to preserve the probabilistic structure of the quantities that you're focused on, not of course the entire response, but of the ones that you need to combine the sub-models into a big model and still produce a reasonably good simulation. So this would be a way to go. Another is just brute force. Get more of the Amazon cluster and just rip it. There is
one of the online.
Yeah, I'll make the PDF available, and where you're going to post it, I guess there is a place for that.
Final question. Right, please join me one time. Thank this year's
Thank you.